one rather suspects, well, we know, I won't go into all that. Others have done it much better. Right, here's the issue. Is CO2 the most dangerous gas on the planet, which is what seems to be the implication? A colourless, odourless, life-giving gas, an essential building block for all life. As we all know, we are made of it. When we burn fossil fuels, I've got a piece here, I put it in a plastic bag, it's a lump of coal now, and we set fire to it. If it's oil, I couldn't illustrate gas very easily. It tends to be a little bit difficult to see. When we set fire to it, it makes stuff like this. And I remember writing to Michael O'Leary, who runs Ryanair, the Irish pilot who runs Ryanair, telling him that, roughly speaking, a ton of aviation fuel produced 1,500 loaves of bread. He rather liked that. No reason why you shouldn't think like that. There has been, in the last 35 to 40 years, and this is obviously a bit approximate, something like a 20% increase in the global biomass, because, of course, of the slight increase in CO2 causes vegetation to grow, and that's encouraging, it seems to me. One of the reasons why I say cutting carbon kills, because if you actually try to cut carbon dioxide, people who are living on the edge between survival and unsurvival will go over the edge because their crops will fail. So it's a form of genocide without, I mean, I'm not accusing them of deliberately doing that, they just haven't thought these things through. Here is a photograph of the greening of the Sahara from the south. The trouble is I haven't got an earlier comparison, but nonetheless it is greening from the south at the moment, which can't be a bad thing. One of the things about more CO2 with plants is that actually they require slightly less water to grow. Because the stoma, the little mouths on their leaves that open to draw in and transpire out water vapour, don't have to open and close so often if there's more CO2. So they lose less water vapour, so they use slightly less water. So there's a double whammy advantage for more CO2. You can grow more, and you don't need quite so much water per unit. So that's an added advantage of more CO2. Now, the question of it's all getting dreadful, CO2 has reached 400 parts per million, we're all dead. An idea, this is Coles to Newcastle here for most of you, you'll know all this, but one way of looking at it, if you imagine 2,500 people around their little heads and shoulders of being the atmosphere. Of that, 79% of them is nitrogen, around just a 20% or under is oxygen. The next most common gas is argon, at 1% of the atmosphere. Then, in relation to all this, that little gentleman there, little red man, is the representation of the amount of CO2. How much do we contribute, inverted commas, to that amount, ballpark? Well, to do that, you have to multiply your panel of 22,500 by 25 in order to find the single man that comes from human emissions. He's lurking there somewhere. Probably can't even. You can just see a little spark of red. That's our contribution. It's just a way of making people realise the actual scale of it. Most people don't know how much CO2 there is. Even intelligent, grown-up people, journalists, they don't know. I'm not saying all journalists, they don't know. A little bit of background here. This is to some degree speculation. Allow me, indulge me a little bit. If we think of the four rocky planets, our own, Venus, Mercury, and Mars, one of the things that's interesting is that it's very likely at the early formation of the solar system, the rocky planets attracted the heavier gases. And of those, of course, CO2 is the heaviest. It's 44, oxygen's 32, nitrogen 28, hydrogen is 2, water vapour is only 18, and so forth. Now, it's interesting to note that the atmosphere of Venus remains at 95+% of carbon dioxide and has an atmospheric pressure of 90 Earth atmospheres at the surface. A lot of the warming on Venus, besides being nearly half the distance to the sun, therefore gets more solar radiation, a lot of the heat on the surface is due to gravitational heating because of the pressure of the atmosphere trying to escape, but it's a squashing process going on all the time. It's interesting too that Mars still has 95% CO2 in its atmosphere, but most of that atmosphere was long ago blown away by the solar wind. And it's got a core, it hasn't got a magnetosphere, as far as I know, and so it's very low pressure, but it's still 95%. Mercury tells us very little because whatever it ever had has long gone, and whatever is there is not worth being relevant. Why does that matter? Now this is where I move into the realm of somewhat speculative. It's not again based on my own ideas. It's based on a deceased geologist called Graham Oram, whom I knew. He died last year, very sadly, rather suddenly. And he put forward this hypothesis that the Earth began its life rather like Venus. Some 100 atmospheres pressure and almost entirely CO2 atmosphere. What happened to make the difference? What happened to make our amount of CO2 to be that? Well, we all know it's life. The cyanobacteria began it and sucked CO2 out of the atmosphere, turning it into organic life and then turning it into oils and gases and so forth, sequestering the CO2 in the biosphere or in the Earth. Now, this is all very simplistic and crude. What they also did, of course, by photosynthesis was to generate oxygen, which to some degree was a poison. From their point of view, it didn't matter. So oxygen increased as the CO2 fell. The atmospheric pressure was also falling as a result of taking the CO2 out of the atmosphere. It ceased to be so much pressure because there was less of it. Then there was what many argue was a global ice ball when CO2 was at nearly 40%. So CO2 obviously causes cooling as opposed to warming, but that's by the by. And out of that emerged, of course, the Phanerozoic age, when life expanded in an extraordinary fashion, emerging from that period. Oxygen was considerably higher, between 40 and 30%, particularly for a very long span of period there. CO2 was falling because of life was drawing it out. Pressure was also falling. However, in the very early period, about 500 million years ago, Carboniferous period, the arthropods, which were things like dragonflies, were huge creatures. 2.5 foot wingspan, in a metre, if you're French, well, 2/3 of a metre. They would have needed not only a lot of oxygen to maintain the energy in flight, they would also need high pressure in the atmosphere to enable them to actually fly because of their weight, body weight, wings proportion. Going further on in time, we have the flying dinosaurs and the flying creatures like that. Once again, they would not be probably able to fly today. Jurassic Park has its problems. We couldn't actually get the pterodactyls up there. They just fall out of the sky like a lead balloon. But of course, the pressure at that period was 3 or 4 times what it is now. And again, the oxygen, which they would need for this extraordinary hot-blooded, because they were hot-blooded creatures, as far as we know, the dinosaurs, they needed that oxygen to keep going. So going back to that, during this long period of high oxygen, 30% plus, these creatures could exist. CO2 was still pretty high on this hypothesis, and there was a logical reason. Oxygen at 30% would spontaneously tend to ignite forests and plants simply because of the high oxygen, the oxidation level. They needed a fire extinguisher, and there was one there, CO2 in the atmosphere. Enough of it to reduce the risks. Welcome. Hi. To reduce the risks of forest fires, even at that period. Aha! Here's welcome. Finally got off the train.
Nice to see you. Could you please change
Mark,
the place with your brother?
Oh, yeah, we're working on that.
Nice to see you. Here's Corbin, weather action. Mark, going to be the cameraman in due course, is that the idea?
Yeah, we have a camera.
I'll get that for the next time.
Yeah, we have
We're being filming at the moment. So.
All right.
Good to see you guys.
It's lovely to see you, but you gave a wrong address.
Oh.
It said Rue Roche.
Oh, well, no, it's
Roche
fruitful
Fruitful
coat.
Coat.
Yes, yes.
Straight up on the piece of paper. All right.
Okay, moving on, the CO2. Then came the impacts which in themselves probably didn't kill the dinosaurs, but what it probably did was to shift the balance of the atmosphere, dropping oxygen from 30% to 20%, and that's what would have genuinely suffocated the dinosaurs over a period of time, but it would have taken time as they struggled with their hearts trying to keep warm and trying to have enough oxygen. So that probably killed off the hot-blooded dinosaurs, but did not kill off the slow, cold-blooded creatures that could manage by simply slowing their metabolism. That's a hypothesis, not a certainty, but it's moving on, which I'm doing. The belief that carbon dioxide drives climate change and that human emissions are greatly increasing this effect rests on the interpretation of three pieces of evidence: the ice core data, the modern rising levels of CO2 from somewhere around 0.03% to 0.04%, and the fall in proportion of carbon-13, a non-radioactive isotope of carbon, in atmospheric CO2. Here is a schematic, really, of the ice core records, with the temperatures in blue and CO2 in green, and methane shifted up at different scales in sort of brown. And the famous Al Gore point was, oh boy, do those things not obviously link together? Well, they do, but if you actually look at the detail, and this is a crude way of doing it, and expand it out, what in fact you tend to see is that over that period, the temperature rises first, and then perhaps some 1,000 years later, the CO2 follows upwards. Remembering that the ice cores are very compressed and very smooth, so they're not going to give you year-by-year stuff at all. And methane follows the same sort of pattern. The likely cause of this is that the rise in temperature is what has generated the the increasing CO2. It's a natural thing, even if you think of it today. If the oceans, for example, warm, then they will outgas CO2. Warm drinks spew out CO2, fizzy drinks, cold drinks don't. It's a point people forget. It's simple, basic physical chemistry. Gases dissolve more in cold water than in hot water. It's the reverse of most chemical salts. However, they claim that nonetheless CO2 was driving the temperature, but in fact James Hansen knew perfectly well that they did not. This is James Hansen speaking to a reporter on the 10th of October 1989. In fact, the CO2 changes do seem to follow the temperature changes, not precede them. That is from the horse's mouth, from the very man who told that Senate committee that we are all going to boil. These are his own words at the same time. And as I said, this is hardly surprising, as warming causes outgassing from the sea and more organic decay on land, a point I shall touch on in a few minutes. This comment was just 16 months after Hansen's infamous declaration to the US Senate that a catastrophic man-made global warming had started. And as some of you are well aware, that was a setup from the start. The Senate room in which this announcement was made had been so arranged. It was in June in Washington, which is a hot time for them. The air conditioning had broken down. People were sweating, literally, and doing this with their shirts. And Hansen told us, we're going to boil. Psychologically, very well done. Well, here we still are at it. Worked very well. Now the ice cores. One or two little points in passing about these. I'm no great expert on this. Here's my magpie business going on again. Here's a picture of them pulling out an ice core. Here's another one as they pull it out, in which you, in theory, can just about see the little bubbles of trapped air that have been accumulating in the ice cores over many hundreds of thousands of years. But a point that is sometimes missed, as I understand it, is that when you take an ice core out of the ground, literally as you're pulling it out of the ground, you have outgassing. Because at the bottom of the core, you've got huge atmospheric pressure. In fact, you've got the crushing weight of ice above it. The pressure on the air inside the ice is huge. Reduce it to 1 atmosphere, the ice cracks, the air gasses out instantly. And I remember hearing someone who does this work, pulling out these ice cores, you can hear them fizzing as they come out of the ground. So in other words, when you measure the gases from the ice cores, you are not measuring absolute amounts. You've lost most of it. All you're probably picking up is a trace shadow of ups and downs. It's a kind of differential of the changes rather than the actual amounts involved. This is partly based on Murray Salby, but on that sort of basis, even going back a few, 100,000 years, we could well be looking at a great deal more CO2 in the atmosphere than is claimed at the moment. 10 times, 20 times, perhaps. I mean, this is, to some degree, obviously, modelling, not measurement. You can't do the measurement, that's the trouble. Quickly through the global carbon cycle, and many others would be able to challenge and say, well, this isn't very good. Obviously, we have ocean, vegetation, and land. The oceans are exchanging CO2 with the atmosphere on vast quantities in both directions. These figures are obviously extremely variable. Sometimes a lot's going up, sometimes a lot's being sucked in, depending on the temperature of the ocean. The same is true on land. Massive amounts of exchange of CO2 between organic material sucking it in and rotting organic material letting it out. And at the same time, incidentally, letting out methane, because anaerobic decay, where there's not enough oxygen, tends to generate methane. Human beings are also doing this. We are burning fossil fuels to some degree and using farming techniques to take it in again, I suppose, arguably. However, the quantities involved in human emissions are order of magnitude at least smaller than the natural processes around us, which accounts for the fact that probably human emissions are 4 to 5% of the total. An additional point here is volcanism. On land, volcanism doesn't generate a great deal in terms of overall amount. It does generate quite a lot. But what we do not know, as I understand it, is ocean volcanoes. And as far as we can tell, there are, again, an order of magnitude more ocean-bed volcanoes and cracks and so on than there are on land. It's difficult to measure, difficult to know. I opine at this point that in the deep trenches there is liquid carbon dioxide. Under cold and under pressure, it liquefies, which tells us something about the oceans as a whole, that a solute in presence of its solvent, of its solute, is saturated. In other words, if there is undissolved CO2 in contact with ocean water, it follows that most of the oceans are already permanently saturated in carbon dioxide. What goes on at the surface layer would obviously be much more complicated because of the disturbances and so on. So that's just it combined, so moving hastily on. Here is, and this is Murray Salby now, I'm just going to spin through this. Here is the temperature since 1958, up to about 2013, 2014. Here in the green is the CO2 emissions. The seasonal jaggedness is what you might expect. If you then get net global emission of CO2 and model it, yes, it is a model, with surface conditions, primarily temperature and moisture, what you tend to find is that as surface conditions fluctuate, so too does the CO2 emissions, strongly suggesting that the CO2 that we see changing and increasing is due to natural emissions, particularly from vegetation, rotting, and so forth. The same is true to the carbon-13 emissions. Do exactly the same. Interestingly, plants do not take up carbon-13 as opposed to carbon-12. They prefer carbon-12. It's a slightly different size atom, so therefore they are slightly picky. And the argument is that because the CO2, the 13 emissions are falling, this is because we're burning fossil fuels, which of course is made from organic material. But of course it's equally true of organic material that is existing now. It too is low in carbon-13 by default. So it doesn't, the fossil fuel argument doesn't hold water. In passing, just like with the CO2 chart, the same model with methane. And one of the nice things that Murray Salby says that the alarmists presumably have to claim that burning fossil fuels causes flatulence. Because if the CO2 and the methane are behaving together, clearly that cannot be, or at least it's unlikely to be simply due to burning fossil fuels. We must be producing more methane as well. Well, I suppose they blame the cows, but there we are. Now, yeah.
Yeah, no, I can see the point.
Interestingly, human emissions from fossil fuels have done an interesting thing. From the 1990s, the rate of increase is that angle, From 2002, there's an almost perhaps doubling to tripling of the rate of increase of use of fossil fuel, mainly because of China and India, but other places as well. That is interesting. This is a step change upward, which you would expect if human CO2 emissions were driving temperature, you would expect that to have an effect on temperature. Let's go back to this for a moment. This is the CO2 temperature and so on, imposing on it a simple version of this change. What is interesting is, of course, one, that the temperature flatlined when our emissions doubled. At the same time, the rate of increase of CO2 slowed up. If you notice here that during the period of warming, the CO2 emissions were increasing on a quadratic scale, a curve upwards. At the point at which things started to flatline, that curving upwards began to become linear. This is what you would expect with a natural model of CO2 emissions from the land and the sea. Very simplified. Here we have it again, the temperature very crudely done, flatlining now, the CO2 emissions doglegging upwards, yet CO2 emissions have slightly declined and the temperature has flatlined. It seems to me it would be unreasonable to conclude that this sudden spike upwards in emissions of CO2 from men, human beings, has anything to do with either CO2 levels overall or temperature. This is borne out by satellites. This is not the satellite picture. This is a calculated picture of where, if human emissions are the cause of the increase in CO2, where you would expect to find, to some degree, accumulations of CO2 over, obviously, the industrial areas of Eastern America, over Europe, India, and of course China being very dirty, and to some degree Brazil. That's what calculated would be. That's a model, if you like. Here is the satellite observations